Welcome back, YouTube. We're on Chapter 5, Section 7, Growth and Decay Models. Okay, exponential growth and decay. So what does that mean? Well, let's take a look straight at the homework page. We got homework page 346 tonight, multiples of 5. Take a look at number 1. It says you're modeling the population of a colony of bugs, and this is the model that you're given to analyze. The question is, what is the doubling time? Well, if you plug in t equals 0, you get 500, right? P of 0 is 500. So the doubling time is how long does it take to get 1,000? Okay, so how do you solve for t? Divide by 500, and there's your growth factor. And it's an exponential growth rate because the 0.02 is positive, right? And then how to get rid of e to the ln both sides. You could use any log, but ln is nice here because the e just goes away. And divide by 0.02. And you could write that, ln of 2 divided by 0.02, but isn't that dividing by 2 hundredths, which is 1/50th? How do you divide by a 50th, a fraction? You multiply the reciprocal, it's 50. And if you punch that into your calculator, we got, in class, 34.657, and t is given in days, by the way, read the question. All right, so how do you check that? Well, you can do it graphically. We did it algebraically, now let's redo the problem graphically. So, let's see, do I have a calculator running around? Come on, calculator, with signal there. Whoopsie, we've got a little lag going on here. Come on, computer. All right, we'll let that cook, and we'll come back and check that in a minute. Then, part B, that was part A. Oh, there it is. Okay, whoopsie. All right, you know what? Let me clear this. Let me clear this. Let me clear this. Second quit. Okay, all right, so let's check this. All right, that's good. So... there we go. All right, so what we wanted to do was figure out what is ln of 2 divided by 0.02, or 50 times the ln of 2. Same thing, right? So 34.657-ish if you're rounding up to 3 places, days. So go back to here, and, well, I wrote it. There it is. Good. Then part B is, okay, how long does it take to get 2,000 bugs? Wasn't that doubling again? An exponential growth model has a constant doubling time, so just double this. An exponential decay curve has a constant half-life. We'll talk about that in a minute. So now don't double this. Double the exact value, so 100 ln of 2, or double all the decimals you can get to be as accurate as possible, because you don't want double round-off error when you round off again. So I'm going to take this, well, I could just do this, times, and the previous answer times 2, and rounds that off to 69.315, which is not the same thing you would get necessarily if you doubled 34.657. Or, of course, you say 100 ln2, or you could say 2 times, just to be fancy, ln of 2 over 0.02. Same thing, so 69.315 days. Okay, that's question 1 on the homework page. Just practice, warm you up to do the homework multiples of 5 tonight on page 346. So in other words, you really know how to do this already. All right, let's do number 3 for practice. All right, you have an amount of strontium-90. They don't tell you the amount, they don't tell you the units, but it's probably something like 100 micrograms or something. That varies over t in years, okay? And you have an initial amount, a sub 0, whatever it is, and the decay factor is this. So notice this is a negative exponent, so it's going to be decay if you graph it. Okay, so the question is, what's the half-life? So if you knew that a sub 0 was like 500, like we had 500 bugs last time, we would set this equal to 250, make it half, right? But the point is that it doesn't matter. You can plug in anything you want for a0 and half of it for a of t, and you'll still get the same time. So how about we just take a0, whatever it is, divided by 2. All right, so in class we figured out first step is divide both sides by a sub 0 to get rid of it. And now you're talking about the growth rate being a half. So how do you solve for t? Okay, let's, well, ln both sides, get rid of the e then. And then divide by negative 0.0244 or whatever, right? So t is ln of a half over negative 0.0244. That's probably an approximation anyway. So what do you get? If you punch that into your calculator, I think you get 28.408 years. All right, let's double check that. So let's graph it. So we're going to graph in, well, let's do the calculation first. It was ln of a half, how about 0.5, divided by negative 0.0244. And notice we get a positive quantity, even though we're divided by a negative number. Why? Because ln of a half is negative. Remember that when you plug in 0 into a log, you get 1. When you plug in 1 into a log, you get 0. If you plug in more than 1, you get a positive result. If you plug in something between 0 and 1, remember, you can't plug in 0, you can't plug in negative. If you plug in something between 0 and 1, remember, it's negative, right? You know what the log curve looks like. That's good. Now let's check it graphically. So let's graph. What were we solving? Well, we were solving this. Right? So how are you going to do that? Well, in other words, this here. How are you going to do this graphically? Well, in A1 and A2, Y1 and Y2, you got to have a certain number here for A0. And again, notice it canceled out, so it doesn't matter what it is. So what if I make A0 100 and A0 over 250 and graph that? All right, so I'm going to graph 50 times e to the negative 0.0244. I'm in function mode, so I can't use t. It's just a dummy variable, it doesn't matter. And, I meant to put 100 there and then 50 here. All right, I'll put 25 here. Now, what's a good window? Well, we're trying to show that it's about 28 years, right? So that tells you that X max should be, say, 30. And this starts at now 50, and it decays from there. So Y max is about 50. All right, so let's do, if you do zoom 4, you ain't going to see anything, right? That's no good. All right, let's stop that. Hit the on key to stop. No. Okay, stop graphing. See that little yellow thing up top? Yeah, okay, there it goes. All right, so let's change the window. So like we said, it starts at, I made it start at 50, and it's decaying from there, so it's never going to be over 50. So Y max is 50 is good, and then it's going to go down. Can you have negative strontium 90? No, you can only have negative people. How about we make that 0? And we said we're trying to prove that T is about 28.8 something, right? 28.408? Yeah. So how about 30? And then can you have negative time? Only if you're Stephen Hawking. So let's put a 0 there. And let's see if this is a decent graph. So there's your decay curve. And let's see where it hits. It's starting at 50. Let's see where it hits 25. There you go. And let's see, I don't know if I like my scale. Let's make a scale here of 10 on the x-axis. And a scale of 10 on the y-axis. So just make it easier to read. All right, so does it look like they intersect somewhere around 28.4-ish. So it's 10, 20, 30. Yeah, close to 30. Okay, so let's see. Second, calc, intersect, enter, enter, enter. And 28.408-ish. Yeah, there it goes. Perfect. Very nice. All right. By the way, we should also check the first question we did. We didn't check that graph. I don't recall doing that. So let's graph y1 is 1,000 and y2 is 500 e to the 0.02x, because I'm in function mode. And see that they intersected around 34.6 something. Okay. So let's change the y's. Let's make this 1,000 bugs. Well, let's clear that. Let's make this 500 times e to the 0.02, and I got to use x because I'm in function mode. Now, notice the window. I'm trying to prove that t is 34.6-ish days, so my x max has got to be more than that, say 40. And I'm starting with 500 bucks, and I want to see it double to 1,000 bucks, right? So my y max has got to be more than 1,000, say, I don't know, 1,500. And the scale maybe of 100, so you can see the tick marks on the y-axis. And whoops, let's show the big screen. And so we're trying to show that the intersection point is at 28.408 years. That's the x value here. And I think so, 10, 20, 30, 40 was my x max, right? So second, calc, intersect, enter, enter, enter. 20, sorry, what did we say? Oh, wrong question. What did we get for the first one? 34.657, right, okay. All right, good. Now, one other little observation one of the students made, who was very astute, is that what if you plug in 2,000 for the second part, with the second doubling time was 69 point something, right? What if you do put in 2,000 here and you work it all the way out again? You could do that. But then when you divide 500 into 2,000, you get 4, and then you end up with the ln of 4 equals 0.02 t. So t is ln of 4 over 0.02. But isn't that double what we had before? Remember, ln of 4 is really 2 squared. And what do logs do to exponents? Brings it down. So it's double what we had. Didn't we say it was going to be ln of 2 over 0.02, or ln of 2 times 50, and then double it? That's why it's the doubling time doubles when you double the population again. Okay, just for fun, there you go. All right, now this is where things got a little hairy. Take a look at number 15. Number 15 says to analyze Newton's law of cooling. Okay? Given the heat content measured, in this case in degrees Fahrenheit, over time, T in minutes, is equal to T, the room temperature, the ambient temperature, plus the initial temperature of your object minus the room temperature times e to the k, T, where k is negative. So it's a decay rate, okay? Now, to give you some information, you're cooking a pizza. You take it out of the oven. At T equals 0, it's 450 degrees Fahrenheit. So this is T versus H. We're using degrees Fahrenheit or temperature to measure heat content, right? Then 5 minutes later, it's cooled down to 300 degrees. Question is, when is it safe to eat? What's T when the pizza is 135 degrees? Apparently it's too hot otherwise, and your teeth fall out if you eat it. Okay. So what do? Well, let's plug in what we know. If you read the whole question, it also says that the room temperature is 70 degrees Fahrenheit. H0 is the initial temperature of the pizza, so 450 minus T is still 70. E to the KT. So you're trying to figure out T when H is 135, but you can't do that until you know K. So how are you going to get K? Let's plug in, so we basically used this point already, see the 450? Now let's use this point to figure out the K. Plug in 300 for H, plug in 5 for T. By the way, 450 minus 70 is 380. And you got to solve for K. All right, so how do you do that? Subtract 70. Divide by 380. And I reduce by 10. Get rid of the e to the, as you know. That means I'll ln both sides. And divide by 5. So there's your decay rate. Now notice, I don't care what the decimal version is here because I'm going to use this exact value. You can give me a decimal if you want. But I'm going to use that exact value because I'm not done. That's not the question. The question is, what's T when H is 135 using this value of K? All right. So I'm going to go back to the beginning, and I'm going to rewrite this with the K that I figured out. Then I'm going to plug in 135 for H and solve for T. Okay. So here's like part 2 of the question. So now we know that the heat constant, H is measured in degrees Fahrenheit over T minutes, is 70 plus 380 e to the K. Now K was 1/5 ln of 23/38 times T. Now remember that K, that number in front of T, is supposed to be negative. Is it? Yeah, because it's the ln of a number less than 1. We talked about this. Okay. So let's plug in 135 degrees here and see when it's safe to eat. In other words, solve for T. So what are you going to do? Subtract 70. Divide by 380. Which you could reduce, what? This would be 30, this would be 1376. Leave it like that, that's fine. Whoops, I didn't ln yet. And then ln both sides. That gets rid of the e to that. And then divide by 1/5, which means multiply by 5. And divide by the ln of 23/38. And And again, I'm greedy. Give me the exact answer and the approximate answer. Now, I got 17.584-ish minutes in class. Let's double check that. All right, so wake up, calculator. There it is. Okay. All right, so let's clear this. So I want 5 times the ln of 65 over 380. That, in turn, divided by the ln of 23 over 38. I'm not using the alpha y equals 1, but it could have, I guess. And that's about 17.584. Now they said solve it graphically. Check by graphing. Okay, so what are we going to do? We're going to graph this. Let's make y1 135 and y2 the right-hand side of the equation and see that they intersect. And now remember, this thing starts at 450 degrees and it's cooling off to room temperature. It's not cooling off to 0. It's not exponential decay. It's exponential approach to room temperature. And it takes about 17 minutes. So you know what your x-max is, over 17 minutes. You know what your y-max is. 450 is enough because we're decaying from there. All right, good. So if you got a good window and you know what y1 and y2 are, just find the intersection point, right? So there's this, y equals. All right, so here, trying to get to 135. Here I have 70 plus 380 e to the, all right, let's get fancy. Alpha y equals 1, or rational, 1/5 of the ln of alpha y equals rational, 23/38. And, whoops, I don't need that. And again, remember, I can't use t here. I'm in function mode. I've got to use x here. Now, let's get a good window. We're trying to prove that it happens around 17 minutes. How about make it 20? And you don't. It's never going to get warmer than 450. It starts at 450 and gets colder. And that's why we have a good window. So there's the y equals 135. And here is your Newton's law of cooling. It's a exponential approach to 70. It's not an exponential decay, which means it's going to 0. And does it, it's going to 70, but I'm trying to say, when does it hit 135? Okay, so, intersect, and enter. Yeah, 17.584. By the way, it is approaching 70 asymptotically from above. The limit as t goes to infinity is h equals 70. Is that right? Let's see, is it trying to approach 70? Let's see. Well, it's hard to see there. Let's make my x-max a little bigger. How about 200 minutes? Is it going to approach the green line, y equals 7? That's what this should show. Is that 70? What it's a horizontal asymptote of 70, right? That's what Newton's law of cooling looks like. It's trying to approach the room temperature with 70. There it is, right? Perfect. Okay. All right. So let's get rid of that. Let's put that back the way it was. I'm going to get rid of the 70 for a minute. I'm going to put this back to 20. All right, then that's part B of the question, is checking your work graphically. Part C of the question is, at what time is the temperature of the pizza not 135 degrees, but 160? I guess you're a He-Man and you can eat it sooner at a hotter temperature. I don't know. So what do? I don't want to know where the red curve hits the blue curve. I want to know where the red curve hits the green curve if I make y3 160 degrees. So how do you figure that? Same way. Second, count, intersect, but I don't want the blue curve. I want the green and the red. So up arrow, green, up arrow again, red, and then enter. And that's going to be 14.344-ish minutes. And that's what we did today. So that should make the homework easy, I hope. A little warm-up for the homework. That's basically what the homework looks like. So page 346, multiples of 5 tonight. Have a nice day. Bye-bye.